Hello, this is Aloisa with Math Leopard. Today I'm going to cover the generalized divisibility test for integer divisors d such that d is neither a multiple of 2 nor 5. To begin, let's consider n equals to 53,599 and have this be our given number we wish to find a divisor for. The second step is to consider a number d for our divisor, say 13 in this case, which is neither a multiple of 2 nor 5, and to test to see whether it divides 53,599. Next, we multiply d by an integer k such that the final decimal is 9. In our case, k equals to 3 suffices, leaving us with a product of 3 times 13 or 39. Step 4 is to add 1 to the result from step 3, thereby creating a multiple of 10. Step 5 is to eliminate the terminal 0 of the result in the previous step by taking the floor of 1/10 its value. The result is 4, which by construction is an integer. Let's call this integer m. Hence m is equals to 4 and is our key for the remainder of this process. The next step is to eliminate the terminal decimal of 53,599 by dividing through by 10 and taking the floor, resulting in 5,359. However, we take note of the final decimal in yellow, 9 in this case, as we use it for the next calculation. So taking that final digit 9, we multiply it by our key m above, that is 4, yielding 36. Finally, we take the sum of the results in the final two steps, 5,359 plus 36, and arrive at 5,395. Is this a multiple of 13? That is it an integer multiple of our divisor d? I can't see at this point, so I'm going to continue the process above, but only require steps 7 through 9 with the result from our previous test. Taking 1/10 of 5,395 and then the floor of the result leaves us with 539, truncating the decimal 5, where 5,395 comes from the result in step 9 to the left, seen here in pink. Next, we take the decimal 5 and multiply it by the key m equals to 4, which we found in step 5. This results in a product of 20. Finally, step 9 is to sum the results from the previous two steps, namely 539 and 20, resulting in 559. But can we readily see if this is an integer multiple of our potential divisor d equals to 13? Not at this point. So going around again, I take the floor of 1/10 of 559, resulting in 55, with the decimal of 9 seen here in yellow, where 559 is the result from our previous attempt in green to the right. Next, I take the product of that truncated yellow 9 above and our original key m equals to 4, resulting in 36. Finally, we take the sum of the results from the two previous steps, arriving at 91. But is this an integer multiple of d equals to 13? I'm still not certain. So let's continue the process yet again. Taking the floor of 1/10 of 91 leaves us with 9. The decimal we truncated was 1, seen here in yellow. Next, we find the product of the truncated yellow decimal 1 and our key m equals to 4. What results is 4. Finally, taking the sum of the results for the previous two steps gives us 9 plus 4, or 13 exactly. 13 is clearly an integer multiple of 13. Therefore, 13 is indeed a divisor of 53,599, using tests 1, 2, 3, 4 times over. Now let's consider another number, say n equals to 95,381. This is our given number. I would like to know whether d equals to 29 is a divisor of n. I multiply my divisor by an integer k such that the result has a final digit of 9. In this case, k is equals to 1 because 29 already ends with 9. Now we add 1 to the result from the previous step and arrive at 30, an integer multiple of 10. We then take 1/10 the previous step, resulting in the integer 3. We call this result m equals to 3 our key. Step 7 is to truncate the final digit of the given number m by taking the floor of 1/10 of n. For us, that results in 9,538 once the decimal 1 is truncated. We now take the product of the truncated yellow 1 and our key, m equals to 3, resulting in 3. Now take the sum of the results from the previous two steps, leaving us with 9,541. But is this an integer multiple of the alleged divisor 29? I have no clue. So let's repeat the process again. Taking the floor of 1/10 of 9,541, we're left with 954 after truncating the decimal 1, where 9,541 is the pink result to the left. Next, we take the truncated decimal 1 and multiply it by the key m equals to 3, resulting in 3. Finally, we take the sum of the results from the previous two steps, giving us 957. But is this an integer multiple of 29? I'm still not sure, so let's continue the process again. Truncating the final digit of 957 leaves us with 95, where 957 is the result in green from the test above to the right. We now find the product of the truncated yellow 7 above and the original key m equals to 3, giving us 21. The sum of the previous two steps gives us 116. But is this an integer multiple of 29? I'm not quite certain, so I'm going to do the step once more. Step 1, truncate the final decimal of 116, leaving us with 11. After truncating the 6, where 116 is the result in light green from the previous test to the left. Step 2, multiply the truncated decimal 6 with the key m equals to 3, resulting in 18. Finally, taking the sum of the results from the previous two steps gives us 29 exactly. Therefore, 29 does indeed divide 95,381. Once again, this took us 1, 2, 3, 4 tests to determine, but we're becoming more proficient with the method, so let's give it a final go with the integer n equals to 25,707. I would like to determine whether d equals to 41 is a divisor of n. I multiply d by an integer k such that the result has a final digit 9. In our case, k equals to 9, resulting in 369. I then add 1 to the previous step, yielding 370, an integer multiple of 10. Next, we truncate the final digit of 370, resulting in 37, and name this our key m for this whole process. Now let's begin our familiar three-step test. Truncate the final digit of our number n, resulting in 2,570. Next, multiply the yellow truncated digit 7 with the key m equals 37, resulting in 259. Finally, taking the sum of the results from the previous two steps gives us 2,829. Is this an integer multiple of 41? I haven't a clue. So let's repeat the test again. Truncating the final digit of 2,829 results in 282, where 2,829 is a result in pink from the previous test at left. Next, we find the product of the truncated yellow 9 and the key 37, yielding 333. Ah, what a lovely number. Finally, we take the sum of 282 and 333, giving us 615. But is this an integer multiple of 41? I'm still not sure, so let's repeat the test. Truncating the final digit of 615 leaves us with 61, where 615 is a result from the previous test at right. Next, we find the product of the yellow final digit 5 and our key 37, giving us 185. Finally, the sum of 61 and 185 is 246. But is this an integer multiple of 41? I don't know, so let's repeat the test one final time. We truncate the final digit of 246, leaving us with 24, given the result 246 in light green to the left. Next, we find the product of the truncated yellow 6 and our key 37, yielding 222, another lovely number. Finally, the sum of the two previous steps gives us 246, which is where we began the test before. However, it should be clear to see that this is 6 times 40 plus 6 times 1, or 41 times 6. Hence, 41 does indeed divide 25,707. Note, in this case, only 3 turns of the test were needed, as any test beyond that will cycle back to 246. But all of this is conjecture until we prove that it does indeed work for all divisors d of n, where d is neither a multiple of 2 nor 5. So let n be the sum, as our index counts from 0 to m, of 10 to the index times a sub index, that is a sub m times 10 to the mth power, plus a sub m minus 1 times 10 to the m minus first power, plus dot dot dot, plus a sub 1 times 10, plus a naught. I'm expressing the constant coefficient a naught in yellow of this polynomial in 10. Next, let's truncate the final digit by way of taking the floor of 1/10 of n. This yields a sub m 10 to the m minus first power, plus a sub m minus 1 10 to the m minus second power, plus dot dot dot, plus a sub 1, effectively reducing the power of 10 by 1 in each term. Going forward, let's suppose that d does indeed divide n, and kd plus 1 is an integer multiple p, our key, of 10, where k is a positive integer. This implies that the sum of the truncated integer n and a naught times p, the product of the truncated decimal and the key, is equals to a sub m, 10 to the m minus first, plus a sub m minus 1, 10 to the m minus second, plus dot dot dot, plus a sub 1 plus a naught times p. Now let's multiply this through by 10, raising the power of 10 in each term by 1, yielding a sub m times 10 to the m, plus a sub m minus 1 times 10 to the m minus first, plus dot dot dot, plus a sub 1 times 10, plus a naught times 10p. Let's call the underbraced expression v and rewrite the final term of the expression as a naught times kd plus 1, where kd plus 1 is equivalent to 10p by our supposition. Distributing a naught inside the parentheses and regrouping so that the final term is a naught times kd, what results is the sum of n and a naught times kd. Since by assumption d divides n, there exists a positive integer u for which n is equals to u times d. Rewriting n as u times d gives us u times d plus a naught times kd, which is equivalent to 10 times v above. Let's factor out the common d, giving us d times the quantity, u plus a naught times k, which of course is equals to 10v. This implies that d divides 10, or d divides v. By construction, we know that d is neither a multiple of 2 nor 5, hence they are relatively prime. This entails that d is relatively prime to their product as well, 10. Therefore, d must divide v, which is equals to the floor of 1/10 of n plus a naught p. That is, our divisor d divides the final sum in each test we did. Check mark. Going backwards, suppose that d divides v. This implies that d divides 10 times v, equivalent to n plus a naught times kd. d divides each term in this sum, hence d divides n. Check mark. Therefore, we can use this test for all possible divisors d of a given integer n, where d is neither a multiple of 2 nor 5. Thanks for playing. If you're interested in private tutoring and live in northern Los Angeles, please let me know in the comments below. I'll see you next time.